Okay, hi there again, crew, and welcome to another episode in the Geology 101 Physical Geology video series. I am Geology Professor Sean Wilsey. Thanks for joining me today. And in this episode, we're going to look at how geologists are able to determine the specific or absolute ages of rocks. A lot of times on field trips, you might be with a geologist like me that's telling you that the granite is 32 million years old, or this unit over here is 1.3 billion years old. So we're going to look at a little bit at some of the techniques, the processes, the chemistry, if you will, that govern and help us determine those specific ages. As always, remember that this video series is based on my college course. It's the same curriculum, largely the same material that I present to my college students. Also, with this specific episode, I know many of you are much more knowledgeable than I am about chemistry and physics, and so please just bear in mind that this is a 101 level course, and while this is not necessarily my field, the deep dive in the chemistry and such, but just kind of keep in mind that it is 101 level. So hopefully that is just worth stating there. So let's get right to it and look at what we're looking for here. What we're looking for is some sort of clock, something that lets us know that the rock has quote unquote been born or has come into existence. This rock now exists, and we want some sort of clock to start so that later, many years later, often, when we come around as humans, we can find that rock, perform some sort of analyses, and be able to quantify the age of that specific rock. And the thing that turns out to be the most useful here is this thing called radioactivity, just these unstable atoms, or these things we'll talk about called isotopes, where these particles decay into something else. So there's a change from one atom to another, and by looking and measuring how much we have of one versus another, we're able to quantify and actually calculate the age of the rock. Turns out when we think of all the rocks that are out there, the igneous, the sedimentary, and the metamorphic rocks, turns out the most useful in many instances are the igneous rocks. If you think about it, all igneous rocks have the same fundamental history. They all start as magma or lava, and that material ultimately cools and crystallizes. It might be very quickly if it's coming out of a volcanic eruption, or it can take some time if it's underground cooling much more slowly. But all magmas go through some sort of cooling process where at some point the chemistry is locked in, the atoms aren't able to move and migrate anymore, and that's essentially when the clock would begin and when we would be able to date the actual age of the rock, is that actual moment in time. Sedimentary rocks, it should make sense that most sedimentary rocks are not going to be very helpful because a lot of sedimentary rocks are aggregates of fragments of existing rocks. So think of a conglomerate where you've got chunks of other rocks maybe carried down a river system and then later all glued together. If you date each one of those particles in that rock, it's going to give you a variety of ages. And then the metamorphic rocks are helpful to some degree, but typically the metamorphic process sort of resets the ages. A lot of times the metamorphic conditions are such that the chemistry of the minerals changes enough that it actually resets the clock, and so you're not really dating the age of the original rock or the parent rock, you're actually dating the metamorphic event. And so these igneous rocks prove to be very helpful. Many of the minerals we find in the igneous rocks contain radioactive elements, and then the assumption we make and that we try to make sure we're careful of when we're sampling is a closed system. So for example, I would not just go pick up some random piece of granite off the ground and then send that in for analysis, because I want to make sure that the uranium or whatever the radioactive element is in my rock, that it hasn't had any other new sources of uranium transported inside that rock since that rock formed, since it cooled and crystallized. We're trying to date the original formation of that rock, and so any subsequent event where that radioactive element can be brought in, that can change the results. Now, luckily, we can oftentimes cross-check those ages with other isotopes and see if we get agreement therein. But we do want to make sure that the system we're looking at is a closed system. So I would not want to sample a highly fractured granite outcrop where I think a lot of fluids have moved through that rock since it formed. So those are some of the caveats there determining absolute ages. So we're going to go a bit into chemistry, just a little bit if you will. So most of you may have had some chemistry in the background. If not, we'll just review a bit here. So all atoms have protons and neutrons and some sort of nucleus, and then there's a cloud of electrons that surround that nucleus. And so when we look at our elements, everything that we find in the universe, not just on Earth, we have arranged those elements into a nice handy dandy periodic table, which I'll show you in a second. But basically all the elements we find are defined by the number of protons they contain. So for example, carbon has an atomic number of 6. That means it has or contains 6 protons. And that really is what defines carbon. If you were to add another proton to this and this became 7, that would make it nitrogen. So it actually changed the fundamental element that we're looking at here. So elements are defined by the number of protons in their nucleus. We could look at something like potassium here, which is element or atomic number 19. And then there's another number associated with each element, and this is what's known as the mass number or the atomic mass, which is fundamentally the number of protons and neutrons. It's actually a weighted average of all the various forms of that element. But typically your run-of-the-mill, more stable ones tend to be the most dominant. And so the mass number can vary a little bit depending on some different factors here. So again, to review, the atomic number dictates the element. That's the number of protons. But the mass number is the number of protons and neutrons. So in this case, if we round this off to 39, if we have 19 protons, that means we have to have 20 neutrons in order for this to be 39. Well, it turns out, there's our periodic table, so you can look that up everywhere. This one's nice and bright with vibrant colors, but this is how we make sense of the elements we find in our universe. And some of these are actually synthetic elements. Chemists continue to find innovative ways to actually essentially jam another proton into the nucleus and synthesize new elements. But many of these are naturally occurring, so they're of interest to geologists. And then the really important thing here are these things called isotopes. These are forms of an element, but they have a different mass number. So a good example here might be potassium 39. Okay, which is run-of-the-mill potassium, 19 protons, 20 neutrons, like we talked about. But there's another form of potassium called potassium 40, which still has 19 protons, because that is what defines potassium, that atomic number. But in this case, it would have 21 neutrons. And this form of potassium is actually radioactive, so it's unstable, it decays, and it turns into something else. And the thing it turns into over some length of time is argon 40. So essentially it's turning some of those particles into another type of particle in order to change. In this case, it's turning, I think, a proton into a neutron in order to turn into argon 40. Another example you might have heard of is like carbon 14 dating or radiocarbon dating. Carbon 14 is also radioactive, and it decays over time to another element, in this case nitrogen. So we've talked about radioactive decay. So that's when we have the unstable material or element, what we sometimes call the parent element, and it's decaying spontaneously but at a measurable rate into a more stable particle, which is known as the daughter product. So we have the parent, which is unstable, the daughter, which is stable over time. Why does this have a female connotation? I'm not quite sure, but that's just the verbiage that we've been using for quite some time. The other concept that's important, and one in which I'll do a little thought experiment with you here in a second, is this concept of a half-life. So a half-life is how much time it takes for half of what you start with, your parent element, to decay into the daughter. So if you start out with 1,000 atoms of carbon 14, how long would a half-life be? Well, it's going to be the amount of time it takes for, in this case, if I start with 1,000, I would end up with 500 of those carbon atoms changing into nitrogen. So it's the time it takes for half of what you start with to decay. And half-lives can be measured. They don't change. They are random in terms of the rate at which it occurs, but it's measurable, and over time the averages turn out to be quite robust and very reliable. So here's my little analogy here that'll hopefully be a good one and make some sense. We're going to talk a little bit about popcorn. So everyone knows that if you heat up popcorn kernels, you end up getting popcorn. So consider the popcorn kernels the parent element, and the popped popcorn is the daughter element or the daughter product. So let's say that for Christmas, like for example, I prefer air pop popcorn over microwave popcorn. That's not really relevant here, but let's say you all have been given for a Christmas gift a air popped popper, a little small appliance you plug into your kitchen and add kernels to. And let's say we all have the same brand, same model, and we all start out with, let's say, 100 kernels of unpopped popcorn. So we have 100 popcorn kernels. We're going to all start the clock at the same time, add those 100 kernels to our air pop popper, and then time how long it takes for the first kernel to pop. Now, I would guess that we might have some variation there, but we probably have a pretty tight average. Maybe at someone's house, the first kernel popped at 30 seconds, and at someone else it was 35 or 28 seconds. Who knows what the range is, but I'm guessing it's probably not a huge range. Furthermore, if you looked at those 100 kernels prior to popping them, could you predict which one was going to pop first? And the answer is of course not. You have no way of knowing which one of those kernels really is going to pop first, assuming they all look the same. And yet you have full confidence that when subjected to heat, those kernels will change. They will transform from kernels into popped popcorn that you can eat at some rate. And so that's the idea kind of here. And so imagine now if we could take those kernels and you could add it to your popcorn popper. And if you could somehow freeze frame or freeze in time, this would be very difficult to do, the time in which you have half of your popcorn kernels unpopped and half of them popped. So if you start out with 100, how long would it take for you to have 50 pieces of popcorn and 50 unpopped kernels? And if you could somehow like capture and measure that time, and if everyone did that across the board, we would get a pretty nice tight average there. Who knows, if it's 45 seconds or whatever. And that's the idea here, is that these parent elements are decaying, they're changing into something else because they're radioactive, unstable, and the time it takes for half of them to change is what we call the half-life. So hopefully that kind of makes sense here, because that's the idea here. And so by measuring the amount of kernels to popcorn, if you will, or how much daughter versus parent you have, you can therefore use that half-life to figure out how old something is or how much time has elapsed on the clock since the rock formed in this case. So graphically, this is sort of how it looks. So if we have our parent element here on the left at time 0, so let's assume our initial conditions, we have 100% of the parent element here. After one half-life, by definition, we would have half of that material would be parent, shown in yellow. Half would be the daughter product, shown in blue. After another half-life, whatever length of time that is, we would drop that parent amount again in half. So now we're down in this case to like a quarter, 25% of what we have. 75% is the daughter. And then you can see this dropping. Now this red curve here never quite gets down to the x-axis. It becomes very close to it. It's what we call an asymptote, but it never gets to 0 because you can always take half of something, right? If you start out with 1,000, you take it in half, that's 500, half of that's 250, half of that's 125, so on and so forth. And so theoretically or mathematically, this never goes to 0, but you can get to such small quantities that after about I think it's like 8 to 10 half-lives, there's so little of the parent remaining that it's difficult to measure. And so our instrumentation has a tough time detecting that parent material. And so for practical purposes, you can have so many half-lives go by that isotope is no longer helpful for dating the actual material. And so that's why carbon-14, like for geology, carbon-14 is only useful because if you have organic material that was organic, and because the half-life of carbon-14 is pretty short, like 6,000 years or so, you can only go back about 50, maybe 60, maybe 70,000 years before it's so much time's gone by that there's very little, if any, of that parent material left. So carbon-14 is useful for fairly young geologic features, maybe like lava flows in Hawaii or places where there's been fairly young activity. And we would then also need the organic component. So we would need like a tree that the lava had burned and maybe a little bit of charcoal residue. Then we could do carbon-14 analysis on that. Otherwise, we're going to need much older or excuse me, longer lived isotopes with bigger half-lives, things like uranium-238, uranium-235, potassium-40. Those are going to give us the numbers for things that are in the millions or billions of year range. Okay, so hopefully that makes sense. Again, I'm not a chemist, so that's the best I can sort of handle it. But let's do an example here with a little fun quiz question. So uranium-235 is the parent, and it decays over time to lead-207. Okay, so there's the parent, there's the daughter. The half-life, I rounded this off just to make it simple, is about 700 million years. So let's suppose we find a chunk of granite. Granite contains these minerals called zircon, and zircons contain uranium typically. So let's say in that granite we have a mineral that has about 12.5% of the parent, uranium-235, and 87.5% of the lead. So how many half-lives have gone by? How many of those half-lives have elapsed given the percentages we have here? Remember, we start with 100% of the parent and 0% of the lead initially. So go ahead and pause the video if you need to. Take a minute to try to figure that out. And then let's go ahead and see how you did. So what I like to do is set up a simple table. Which helps me kind of keep track of things. You might be able to do this in your head, but for me it's much more helpful to write it down and keep track visually so I can actually make sure I don't make any mistakes. So if we start here initially with no time off the clock, the initial conditions would be 100% of the parent, 0% of the daughter. If one half-life goes by, then by definition we will have half of that material that was parent decay and turn into the daughter. Notice these always have to add up in this case to 100%. Okay, so I'm down to 50% of my parent and I'm up to 50% on my daughter element. If we allow another half-life to go by, so now 2 full half-lives have gone by, now we have 25% of the parent and 75% of the daughter. So remember, again, these have to add up to whatever you start with. Matter cannot be created nor destroyed. And then finally, in this case, if we go to 3 half-lives, notice we have the 12.5% and the 87.5% that was measured in the rocks. So in this case, we can conclude then that our rock, or the minerals in the rock here, have gone through 3 full half-lives. Well, that's great. So hopefully you got that right. Answer was D. Now the next question is going to be, well, wait a minute, we haven't actually determined how old the rock is. We've just done some cool little math and chemical mumbo jumbo here. So the next question you have, same scenario, everything at the top of the screen here is the same thing as what you just saw. But now we know that 3 half-lives have gone by. So what is the age of the granite? How old is it? And so you have some ages here. Remember, MA is millions of years ago. GA is billions of years ago, mega annum and giga annum. That's the abbreviations we use for time. So go ahead and pause the video again if you need to take a minute to figure that out. You should be able to use the table you just used. I would encourage you to add another column to your table that says time and then figure out the time component needed for each one of those half-lives. So again, pause the video if you need a little bit more time. Okay, so let's go right to the table here. So here is the table, same table we saw before, but in this case I've added a column on the left with time. So initially no time off the clock, no half-lives, 100%, 0%. When I have 50-50 of the parent-daughter, that's 1 half-life, which in this case, with this isotope, represents about 700 million years. If 2 half-lives have elapsed, that would give me 1,400 million years. And in this case, if we have 3 full half-lives that have elapsed, that would give us 2,100 million years, or 2.1 billion years, which would be answer number E here. Well, not number, answer letter E. So E was the correct choice there. How'd you do? Does that make sense? Again, for my Geology 101 class, this is as far as we go. Many of you may know that there's more complex equations and there's different types of, there's alpha decay, beta decay, electron capture. There's more to this for sure that is handled in a chemistry course or in advanced courses in geology. But at the 101 level, this is pretty much where we land with things. One more question for you, one more quiz question if you're enjoying this. It's going to look a little different, but fundamentally it's exactly the same as what you did here. So if you understand where we were with these 2 quiz questions, then I think you'll be in good shape with this next one. Okay, so here we go. So carbon-14 decays to nitrogen-14, parent, daughter. The half-life of carbon-14 is about 6,000 years, again rounding off a bit here. What fraction of the original carbon-14 remains after 24,000 years? Okay, so, and it is worth noting that 5 out of 4 people hate fractions. So when you take 4 people and divide them 5 ways, things can get pretty messy. So go ahead and pause the video if you need to figure this out. I would encourage you to build a table like we did with the previous questions. Okay, let's get right to it. In this case, I'm just going to kind of roll the table out for you. So initially, time 0, no half-lives. We would have the whole, right? 100% of the parent, none of the daughter. Well, another way to represent percentages is just whole numbers, okay? Such that if we have one half-life go by, rather than showing that as 50%, we can just designate that as a half. A half of the original material is parent, a half is daughter. In this case, one half-life for carbon-14 is 6,000 years, so there's our time component. We need to find out how much of the carbon-14, which is the parent, is left after 24,000 years. So we need a couple more half-lives elapsed to see that full 24,000 years, and then we can figure out what our ratios are here. So let's allow another half-life go by. So think about what half of a half is. Well, that's a quarter, right? Or 25%, same thing. And if we have 25% or a quarter of the parent left, that would mean we have 75% or 3/4 of the daughter present. That's 2 half-lives, that's 12,000 years. If we allow another half-life to go by, we take that amount from previously and we cut that in half, so we have an eighth and 7/8 here. Now we're up to 18,000 years. And now finally, with one last and final half-life, we are at 4 full half-lives. We have 24,000 years that have elapsed since this carbon-14 started to decay. And of that original amount of carbon-14, only 1/16 of it remains, and the rest of it is all the daughter product. Obviously, you could keep going. The next one would be 5 half-lives, which would be 30,000 years, and this would be 1/32 as a fraction. So all I really did here, team, was took out the percentages and just turned them into whole numbers or fractions in this case, which everyone loves fractions, right? Hopefully, maybe not. But they're out there. We have to use them from time to time. So I think that's it. So again, just kind of a, maybe not a super deep dive, but a look at how absolute dating is applied to geology, at least at the 101 level. Hopefully you enjoyed this episode. If you want to support the channel, there are links under the video description. There might be 3 little dots at the bottom right of the viewer, and if you hit that, that'll open up the thanks button and you can donate that way. Otherwise, thanks for supporting a channel with your viewership. Appreciate you, and we'll see you in our next episode where we discuss fossils and fossilization. Thanks so much and take care.